So this is Math 1127, Probability and Statistics, Session 3.1. So Chapter 3 is what we call probability theories. So that's what we get into, not statistics, right? Statistics is about, so if you guys recall, it's about the making, so let me in in a layman's term would be the understanding the data or sample that is collected. Right? So if you got collected income data, age or health data, how do we present them? How do we use that information to do analysis to come up with a better conclusion? Probability though is about the theories on what ought to happen. So it's about theories, not based on the data information, empirical data that you already have. Now, in the future, we're going to combine those two disciplines together. But now we're just going to focus on probability. So I want to go through some of the homework problem as I go through this here, just so that you can see exactly what's going on. First, the question is some terminology that I want to go through first. What is a probability experiment? An experiment in probability, right, is basically a design where you have an occurrence of outcomes to be either true or false. So one example would be flipping a coin, right, to see whether or not you get head or tail. Okay, so they had a tail, right? Another example would be rolling a die, right? So you can see what the outcome will be if you roll a die. So that's a probability experiment. Now here's another definition. What is a sample space? A sample space is the collection of all possible outcomes from an experiment. So based on experience we have, based on examples we have, example, tossing a coin, sample space would be, let me see, sample space of a coin toss equals to, there will be head or tail. That's it. That's the only two outcomes you are ever going to get from a coin toss, head or tail. Another example, of course, is the rolling a die, right? Sample space of rolling a die. And there will be 1, 2, 3, 4, 5, 6. Right. In a 6-side, I should say, right, a 6-side die. And some of you guys have die that's like 12-side or something like that. So 6-side, you get 6 numbers, 6 outcomes. So those are the sample space. We denote sample space as, let me see if I can find like a symbol for that. So usually this. Or sometimes in some other textbook, you might see U. So S or U, those are sample space. You just gotta make sure you read the problem to see which one they're using. I usually just do S, but some people use U. But no matter what question you have, right, they're gonna be talking about sample space, definitively. So okay, we got sample space now. So let's answer just a little bit of questions, just to get us started. So right here says, what is the sample space, right? Make it a little bit bigger so it's easy to see. So randomly choosing an even number between 10 and 20 inclusive. So inclusive just means you are including 10 and 20, like you included endpoint. What is the sample space with this thing? Well, what are the even numbers between 10 and 20? 10, right? 12, 14, 16, 18, and 20. Those are the sample space. Those are all the possible outcomes you can ever get. How many outcomes do we have? 1, 2, 3, 4, 5, 6. 6 outcomes. So pretty easy, right? Let's try another one. Identify the sample space for this experiment, which is a game of roulette, and where the wheel consists of, let's say, slots with numbers. There are from 0 to 0 to 1. Now, I never played, I never go to casino, I'm just gonna let you know, right? So, I'm just gonna say that sample space would be this guy. Oh, it would be, I'm sorry, this guy. So, sample space would be 0, 0. So, I guess 0, 0 is an outcome from this game. And like I said, I don't play this game, and somebody, you can email me or text me, if you're good at this game right here. So, from there all the way to 30. Those are the possibilities, right? All the possible outcomes. So there you go. So how many outcomes do we have? Well, here's one way to do it. From 1 to 30, that's 30. Then you add those two. So that's 32. Right. So you can write down a piece of paper if you want to. It's going to be 32. So let's do one more. Let's say determine the athlete sport. So let's look at this, right? Determine the number of outcomes in the sample space. Let's draw a tree diagram. So when you talk about tree diagram, just understand this, right? You have the sport. Baseball, soccer, football, skill is low, medium, and high. So you have basically the different sports, and then you have different skill within that sport. So based on the, as opposed to different teams you can go into, right? You have different level, right? So you can say baseball, low skill, medium skill, high skill, and then soccer, and then football, right? So let's see if this is cool right here. I think that should be it. So now there are how many outcomes? Let's see, 1, 2, 3, 4, 5, 6. So that's 9. And you can think about it this way, right? You have 3 sports, and each sport has 3 different levels. So 3 times 3 is 9. So the tree diagram would be like this. Right? You have those 3 sports right here: basketball, soccer, and football. And you have the 3 different skill levels, right? So there you go. Right, so it's not too difficult, right? So now here's the thing. Let's talk about this another type of question, which is, let's say you have different choices for different items within the same combo, within the same combination. So in this case, right, a restaurant offers a $12 dinner special that has 6 choices for an appetizer. So think about this, right? Now, just to let you know, that $12 dinner special, that 12 means nothing, right? Only thing that matters to us is the choices we have. So we have, so this is 3.1.25. We have 6 appetizers. Right. We have entree, which is 10 choices, right? Like, spaghetti, whatever you got, or fish, or whatever. Dessert, right? You have 5 choices. That's good. So you can choose your own meal in this particular restaurant. It could be like, I don't know, Ruby Tuesday or something. So how many choices can you have altogether, right? How many different combinations can you have? It's actually very easy. All you gotta do is this: 6, right, times 10 times 5. That's it. You have 6 choice appetizer. Each one can have 10, and then 5. So you branch out those choices, so you get 300 different choices, 300 different ways or combination you can get this meal to be done. So not too bad. Now the next one is the access code. So 3.1.27. So the access code says you have 4 digits, but the first digit cannot be 6. the last digit, or maybe the fourth digit, I'm gonna say the fourth digit, must be odd. Must be odd. So the question would be, well, how many different choices do we have to make up this particular access code? Right? Kind of like an ATM pin code, right? Except we have a little bit more of stipulations. So now let's see. I used to do like this. I have 4 digits to choose from. The first I have 4 different digits, right, that I need to pick. The first digits, right, cannot be 6. Now think about, right, how many digits do you have in the universe? Well, look at your phone, right? A lot of people tell me 9, but think about it, right? When you dial your phone number, there's a 0, right? 0 is a digit. From 0 to 9, you have 10 choices altogether. So for the first digit, you have 10 choices except the 6. So you have 9 choices. For the second digit, how many you got? Well, you got 10. Third digit, 10. But the fourth digit is when it gets a little bit crazy. The fourth digit must be odd. How many odd digits do we have? 1, 3, 5, 7, 9, right? That's 5, right? So 5. Multiply them together, and that's your answer. So let me see, what would that be? 9 times 5 is 45. 10 times 10 is 100. So that's 4,500. So 4,500. Yeah. Now let's see about the next problem. Assuming that no questions are left unanswered, how many ways can a 9-question true or false quiz be answered? So that's 3.1, 3.2 ways, right? So you have 9 true or false questions. How many ways can you answer them? So let's see. Now, think about this, right? For each question, you have 2 ways to answer. It's not true or false. So there are 2 ways to answer the first question, right? Well, how many ways can you answer the second question? 2 ways. 2, 2, 2, 2, right? You basically keep on multiplying 2 until you get to the end, right? And we have 9 questions. So think about, right? This is really just equal to, so let me insert an equation here. This is really just equal to 2 to the 9th power. That's all it is. Which is equal to, I don't know what it is, let me say. So use a calculator, right? Calculator. 2 to the 9th power, which is right here. 512. So pretty easy if you know the trick. There you go. Number 7. Now, let's go back to the definition a little bit. So before we establish that about the probability experiment, right? Probability experiment, in our case for this problem, is rolling a 10-sided die. That just means that you have 10 numbers to roll with. So we know right from the start the sample space is going to be 1 through 10. Like this, right? That's a sample space. But now they're asking, what is the probability? What is the probability of an event? An event, right? An event is a collection of specific outcomes that you decide. So, for example, right? I can say an event is, say A equals to, let's just say, stays south of North Carolina, for example. Well, you know, on the East Coast, how about it? On the East Coast, right? So if I say this is the desired events that I have, let's say I go pick a state. I want to pick a state that's south of North Carolina on the East Coast. Well, on the East Coast, I guess you can say there will be South Carolina, Georgia, and Florida, right? And I'm not going to include Alabama and all that. I'm just talking about by the coast, all right? So let's say you're driving down the coast, right? So those are the 3 states. So that is a collection of 3 outcomes, not the whole thing. The sample space is everybody, but we'll just talk about specifically the outcomes that you want. So in our case, right? In our case, the probability of the events that we are talking about here would be, let me just cut that. I'm going to put this to the bottom, okay? So basically, the event that would, let me move it to the next page. This is the events that we wish, right, would be 5. I know this is stupid, but when we go into more complicated problem, it will make more sense. So the events that we want is just 5, just random 5. That's all we want, right? Just one outcome. So then the question is, what is the probability? Well, I know you know the answer. It's 1/10, right? 1 out of 10. But I want to be a little bit more formal. The probability of an event A, for example, is always a fraction. It's always going to be the number of outcomes in A. Oh, let me do this first. So there's always the number of outcomes in A divided by the number of outcomes in S, which is a sample space, right? Right. So maybe I should like this. Is how many outcomes you have in one event divided by all the total possible outcomes. So in our problem, right, is okay, we want 5. That is what we want. So how many outcomes is in this event? Just 1. So that'll be 1 divided by 10, which is 0.1. Right? Or in other words, 10%. Think about it, right? You roll a 10-sided die, you have 10 outcomes to choose from, right? Those are the possibilities. You want to know what is the probability. What are the chances you will roll a 5? That's 1 out of 10. That's 10%. And they want you to use decimal numbers, so just do 0.1. All my tests, I don't care, but decimal numbers a little bit better. Just so I don't have to go and review it. Right? So now, what about this other one? Rolling a number greater than 2 in a 6-sided die. So let's look at this one. So this one is gonna be 3.1.31, right? Now the sample space in this case, right, is gonna be 1, 2, 3, 4, 5, 6. No problem. Well, the events that we desire in this case is a number greater than 2. So we don't include 2, right? It has to be bigger than 2 strictly. So it'll be 3, 4, 5, 6. So now it's the number. Right, so you can do like this. Here's one way you can do it. You can do like the number of events, right, within the event, right, divided by the number of sample space. Right. That's a kind of like a lazy way to say it. So how many outcomes do we have in the event? Which is 4 over and there's 6. Right. Of course, that's not the answer, right? You gotta do 2 over there, so like that. Now, they want decimal number from this, so they want you to round to 3 decimal places. You can of course use your calculator, right? So 2 divided by 3 is 0.67. So they want 3 decimal places, so there'll be 0.667. Right. Not too bad. It's trying to get you to use this particular definition right here, because we're gonna be using that for more complicated problems. So let's see the next problem. 3.1.33. Now, this time they're talking about rolling a lumber with exactly 3 not necessarily unique prime factor. I know it's a mouthful, right? So first, what is a sample space? It's a 8-side die. So now we're talking about 1 through 8. But of course, you don't have to write all of that. Just let you know, right? 1 through 8. The event, I'm calling A, all right? So A, event A. We want to roll a lumber with exactly 3 prime factors, meaning you look at the lumber and see how many prime numbers can divide into that number. So for example, right, 1. What number can go into 1? Just 1. So that's not 3, right? 2, 1 and 2 can go into 2. That's not 3. Let me see. Well, actually, 1. The number 1 is not a prime. Not a prime number. It's neither. 0 and 1 are not considered prime numbers, so let's be more careful. So 3, I mean, now that's going to work. 4 is 2 times 2. Well, that's 2 numbers. 5, 4 is 2 times 2, so 2 and 4. So 2 can go in, but let me see, and not necessarily unique. So yeah, so that's 2 numbers going to 4, so that doesn't work. 5 is 5. 6 is 2 times 3, that's 2 numbers. Let me see, 7, and I want to say that the answer is 8, because 2 times 2 times 2 is 8. So I think the spirit of the question is find that one number that you can factor into 3 different ones, which is 2 times 2 times 2 for 8. This is a ridiculous question, so maybe I should cut that out from the. I'm not gonna put this on the test. So that is 1 out of 8. 1 out of 8. Yeah, I don't like this problem. So 1 out of 8. So that's 0.125. Let's see. Yeah, it is a ridiculous question, but now you know the answer. So now let's see. The next one is 3.1.34, right? Rolling a lumber divisible by 5. So rolling a lumber divisible by 5. Now think about this, right? We have a fair 15-side die, so this time it's 15. So we got this is a sample space now. What is the event? Let's call it A. Now we want a lumber divisible by 5. So that's 5, 10, and 15, right? So that is 3 out of 15, which is equal to 1/5, right? Which is equal to 0.2, and that's the answer. So this one shouldn't be too bad. Just like that. So now the next one is, what is the, so if you look at the table, right? We have a company is determining how prepared people are for long-term power outage, natural disaster, or terrorist attack. The frequency distribution, remember the frequency table we did in the last chapter? Basically asking what is the probability that the next person's survey is very prepared. So let me make it a little bit bigger here. Let's see. Well, I can't do. Let me make this bigger. There you go. So the game is this. We have these guys who answer the survey, right? So the question would be, if based on the data we have, based on just the empirical data, right? What are the chances that the next person would say he is very prepared? So far we have 248. So that will be the number of very prepared divided by the number of all the possibilities that we have so far. So again, don't be shy by using a calculator. you can just go ahead and do 248 plus 926 plus 590 plus this plus this, right? So there'll be 248 divided by 2151. So it's 0.115. They want 3 decimal places, so 0.115 is right. Like that. Like that. So again, not very difficult. You just gotta be able to read the chart and understand, you know, what they're trying to tell you. So number 12 here. So let's see, it's the same thing. The probability of a folder choosing at random is between 18 and 20. That's 5.5 out of the total, right? So I think you guys got it. Just go ahead and add them up and divide. Just remember 5.9 goes first in your calculator. So this is also the same question. Oh, no. So the frequency is a little bit different, but same thing. So this should not trouble you anymore. So that is the end of session 3.1. Thank you for your attention.